So now it gets cool. We're going to start using our rules of mechanisms to predict and understand some organic reactions with some real molecules and show how we can get quite a long way with just some very basic rules. No learning required, just applying simple rules. So, nucleophilic substitution reactions. We're going to be using a nucleophile and substituting the product. In a way, we don't need to know that to begin with. We can just work it out from scratch. How do we apply the rules of mechanism? We look for something electron-rich. Is there a negative charge? No. Are there lone pairs? Well, there's certainly a very good lone pair on this nitrogen. Later in the course, we'll begin to compare, should you use a lone pair on a nitrogen, an oxygen, or a chlorine and get more subtle. This lone pair is very good. And when we're thinking about where it wants to flow to, we're looking for positive charges. Well, there aren't any, but we do have a really delta positive carbon here because there's a delta negative oxygen and a delta negative chlorine. Okay? So let's attack from the lone pair, move the curly arrow to the positive charge, and we have to flow it somewhere good. That could be the oxygen, it could be the chlorine. Let's try the oxygen first of all. It could be either. Now I'm going to keep the main larger organic molecule all in the same place. It's going to make it easier for me to visualize in my head and manipulate. And what we've done is we've made a bond to nitrogen. It has two hydrogens attached still, and an R. It's sharing its lone pair. That means it's developed a positive charge because it's sharing its lone pair. And of course, we've moved electron density onto the oxygen here, so that has a negative charge. We've balanced charge. There was no charge here in the starting materials, and these charges balance out at this stage. Now, we said the charge could either go onto the oxygen or it could go onto the chlorine. So let's see moving it onto the chlorine. Probably an even better place for it to end up because of the electronegativity. So I'll come down here again, keeping the molecule all largely how it was. We now have a double bond to an oxygen because we've pushed electron density back from the negative charge onto the bond. We have lost the chlorine from the molecule, so we'll draw it here, Cl minus. It's come off in the form of Cl minus with a pair of electrons, and that nitrogen is still attached with its two hydrogens and its R group. And of course that nitrogen still has a positive charge. It has 4 bonds coming out of it. It's sharing its lone pair of electrons still with the carbonyl. We're not finished in this process. We flowed the electron density into the delta plus, put it onto somewhere good, which was eventually the chloride ion. Now what can we do next? Well, we have a Cl minus. That is a good place to start a curly arrow. Where's it going to flow? Towards a positive charge. Will it go directly to the nitrogen plus? Well, this nitrogen has 2, 4, 6, 8 electrons. It doesn't want to get loaded up to 10 electrons. We're going to attack something adjacent to the positive charge. Pull something off and give the nitrogen its lone pair back. And if we attack that H and pull that off, because protons are very easy to pull on and off molecules, it's just an acid-base reaction. Here the chloride is a base, this H delta plus is an acid. Then we can get through to CO, NH, R, and HCl. Looks like a good byproduct. And what we've done is we've made, in this case, a secondary amide. We haven't learned the reaction, We haven't learned that an amine plus an acid chloride makes an amide. It might be a reaction that you know from A level. It might be a reaction you've never seen before. But we haven't had to learn it. We've simply used curly arrows to work it out. And we could do similar things with slightly different nucleophiles and work out what the products of those reactions would be as well. We're not limited to just learning that this must react with that. This kind of thing can react with that kind of thing. Okay? Now, you will revisit in detail reactions like this in the carbonyl chemistry course. You'll come back to it and you'll talk about it a lot more. This is just an introductory lecture, but I'm showing you that basic principles will underpin all those reactions that you'll see later. Now, there's a you do the work section here that's quite intriguing. This is a highly toxic compound that's been used as a weapon. See if you can find out what it is. See if you can find out when it's been used. See if you can work out or find out why it is reactive and try to draw a mechanism for that process. You will see some similarities to what we've just been talking about, but you will see some differences as well. But curly arrows are your friend, and they should allow you to work out the basics of why this is such a toxic molecule. That overall, the reaction that we talked about there, I should say, was a nucleophilic substitution because we substituted a chlorine for an amine. We ended up with this nitrogen where the chlorine was. We substituted it, and this was our nucleophile. So that's where the classification of the reaction comes out once we've worked out the mechanism. But I want to show you that rather than learning these are all nucleophilic substitutions, we're just going to work out the reactions. Let's think about some nucleophilic addition reactions. So here is an example of a reaction, and we've now got two reagents. If I show you two reagents, use them one at a time. Don't use the second one until you've finished with the first one. Okay? Now let's think about what sodium cyanide is. It's Na plus C triple bond N minus, and that minus must be on the carbon because it only has 3 bonds here. It must have a pair of electrons left over. So we're looking for our curly arrows. Where's our source of electron density? It's where the negative charge is. Here's the negative charge. Where are we going to flow the negative charge to? Well, we'll flow it to a positive charge. Well, there is sodium, but it's already there. It's already with the sodium, so there's no benefit. That's not a reaction. That doesn't get us anywhere, right? So we'll flow the negative charge to this delta plus. Push it in. Of course, the electron density has to end up somewhere good. That's on the electronegative atom. That's the oxygen. And so what we end up with, again, leaving everything intact, is O minus C N. Like this. And it's worth noting that that sodium plus will like to go and sit with that O minus in just the same way that it liked to sit with the Cn minus, okay? It's just a counter ion. Generally speaking, in organic chemistry, we're not very interested in inorganic counter ions, and we just ignore them. They tend to sit with the bits of the molecules that we're interested in, but not really participate. So we've used the sodium cyanide. Now we're going to bring it into contact with water. Worth saying that very often in organic chemistry, you do what's called an aqueous workup. You do a reaction, then you shake it all with water. So very often there is a second step where water kind of works up and finishes off your reaction. That's really what we're doing here. Now, if we think about water, it's delta plus on the hydrogen and delta minus on the oxygen. Thinking about a mechanism, we're going to start the most electron-rich thing. That's the negative charge. Where's the negative charge going to want to flow? Towards a positive. Well, it's already with the sodium, so that doesn't really help. But it can flow towards a delta positive, and there's a delta positive hydrogen. And then, of course, the electrons have to end up somewhere good on the electronegative oxygen atom. And so what do we end up with here? OH. We've protonated that oxygen, acid-base process, and I'll now draw the CN up here, a cyanide and an alcohol, so-called cyanohydrin functional group, and we have OH minus left over, and for those of you that like to follow such things around the mechanisms, that's where the Na plus will end up, quite happy with the hydroxide. So we're not making the sodium unhappy by moving these ions away, because it ends up with an ion at the end of the day. This is a nucleophilic addition reaction, because we have added a cyanide to the molecule, but we haven't got rid of the oxygen. The oxygen is still there at the end of the process. Let's look at another one. In this case, we've got a different kind of electrophile. We have an epoxide. And before you do this, I'm going to set you a bit of a quiz. On that epoxide, there are 2 delta plus carbons. Our sodium hydroxide is Na plus OH minus. Our mechanism is going to start from the OH minus. Is it going to attack the one on the left or the right? Vote now in the multiple choice quiz. So, what I'm hoping you said, the right answer is that it will attack the one on the right. Why will it do that? This is the first time we've had really a choice. So what kind of factors decide the choice? Well, firstly, it likes the one on the right because it's less sterically hindered. So you attack the less hindered carbon. The nucleophile can get in. This is what we call a steric argument. Also, it is more delta plus. Why is it more delta plus? Because it doesn't have this methyl group pushing electron density towards it. So there's no Me group. And that kind of argument is what we refer to as electronics. So it's more delta positive and it's less sterically hindered. I think a really good analogy is it's like you go into a bar, right? And this is before social distancing and all of that. And you go into this bar and you look at the bar and the right-hand end is really empty and the left-hand end is packed. Where'd you go? You go to the right-hand end of the bar where it's nice and empty. Sterics. But then it's even better than that. It's like your dream bar, because at the right-hand end of the bar, the beer is only £2.50 a pint. Whereas at the left-hand end of the bar, the beer is £3.50 a pint. Of course you're going to the right-hand end because the beer is cheaper. That's an electronic argument. So this epoxide has fewer people and cheaper beer on the right-hand end, so that's where the nucleophilic OH- chooses to attack. This is a more electrophilic site in terms of the definitions you were dealing with in the last lecture. So let's draw the product, and that's not so easy, right? We'll keep the structure of the epoxide intact. It makes life easier. We attack in. We have to push the electron density somewhere good. So that's onto this oxygen atom. That's broken that bond in the epoxide, and it's made a bond here to the OH. And it's put electron density onto that oxygen. I realise this looks really horrible and the bonds look all a bit crabby, but it's easier to draw. You might find that it's easy to put numbers on to start with. You might want to go 1, 2, 3, 1, 2, 3, especially when you're working with skeletal diagrams for the first time. Keep a track of where your atoms are. Oh yeah, that oxygen is still attached to atom 2, but it's no longer attached to atom 3. We've made a bond with atom 3. In this example, it's not too complicated, but if you get up to 6 or 7 atoms in your molecule, keeping track of where they all are is worth doing. One of the big errors people make in exam questions is losing carbons from their structures. Second stage of this, expose it to H2O. Of course, the Na plus is floating around here, but I'm not going to show that now. O minus going to attack the H delta plus, just like so. And that's going to make that OH, and that OH. And I've neatened up the drawing a little bit to make the bond angles look a bit more reasonable. While I've done that, 1, 2, 3 carbon atoms as a check, OH on carbon atom 2, OH on carbon atom 3. So, did you know you could make a diol from an epoxide? No. Have I taught you that you can make an epoxide from a diol? Not really. Have we worked out that we can make a diol from an epoxide? Yes, we have. And that's the point of mechanism. You can see two reagents and predict, work out what they're going to do. And where, like in this case, there are two bits of a molecule that could have reacted and only one does, we call that regioselectivity. Which region of a molecule is going to react with the reagent? The final bit of this screencast is a chilly challenge. You do the work. That means it's super tough. And this is part of the synthesis of propranolol. That's a beta blocker drug used for patients with heart problems. And I think you're now at a stage where you can propose a mechanism for each step of that reaction and predict the reaction outcome. Use the base first, work out what that does, then introduce the second reagent, and you should be able to make this, and then that should react with this. And of course, you can look up the structure of propranolol online, which will help guide you in drawing the mechanism if you're a little bit unsure of what should be happening there. So have fun with the you do the work. Next time, in the next screencast, we'll be thinking about some electrophilic reactions.